Hello everyone. In this video, we are going to have a practical experiment regarding the BJT amplifier response. Okay, what is the objective of this experiment? The student should be able to study that the frequency response in the single stage common emitter BJT amplifier, the low and high cutoffs, and the bandwidth of the amplifier, and the effect of large external capacitor on F low. Okay, because from our previous studies that the output amplitude falls down at low frequency due to the large capacitors. What are those large capacitors? The coupling capacitor and the bypass capacitor. And also, due to transistor internal capacitor, the gain will fall at high frequency, right? So, and also we had to determine the bandwidth, okay, and the mid-band gain. The mid-band gain and also the bandwidth of operation. And we had to plot this, what is F low and F high or in this situation. Now, this is our circuit. As you can see, there are some changes in the values, right, from our previous BJT circuit. Now it has been changed to 1K, R emitter, RE is 1K, RC is 5.6. The coupling capacitor was reduced from 22 micro to 1 micro only. We tried to reduce that, but the emitter capacitor now is 100 micro, and our load is now 5.6, keeping the same R1 and 470. So we have here voltage source, bias voltage is 12 volts, no longer 15. It was adjusted, so there are changes in our circuit. So at the beginning, always we try to determine the biasing condition of the circuit. So we determine BB, BE, BC, IC, IE, IB, and try to verify if it is in active mode, and also compute the value of beta, and also compare the measured bias point. And then you can analyze those readings, and then after that we had to apply a 10 millivolt sine wave, okay, and our frequency we are going to vary from 10 hertz to 10 megahertz, and we will try to determine the F low and F high. What are the F low and F high from the reading? We are going to complete this table. So we will vary from 10 to 10 mega, but our table only requires from 50 hertz, we will vary the frequency up to 10 megahertz. So we will try to determine what are the outputs as we change the frequency, okay? As we change the frequency. Now let us go now to our circuit. So here in front of us is your circuit, okay? This is your circuit. So this is now 1 micro. This is our transistor 3N 2N3904. This is the emitter side, base, and collector. And also our load here is 5.6. So 100 micro and 1K, right? 1K here, the emitter resistance, and the collector resistance is 5.6K. So now, so we are required to what? At the beginning, we are required to verify the biasing, right? We have to verify BB, BE, BC, and the currents. So let us try to complete this table. First, let us measure the currents. So let me just measure first the IC or IB. You can see here my multimeter, ammeter. So I had to measure this current, base current. Let me just remove this one now, open this. Okay, and try to measure the current in between. So put it in micro. Normally it's micro values, the value is in micro. So what will be our base current? Base current here is 1.5 microampere. 1.5 microampere. So you have to connect it back. Let's put it our record. In our record, we have IC, IB is equal to 1.5 microampere, right? So IB is equal to 1.5 microampere. What about our IC? Our IC here, of course, the range is in milliampere, right? So you have to open this. Let us try to measure what is the value of our IC. IC now, okay, is 0.47 milliampere. That means 470 micro, right? 0.47 milliampere, that will be IC, 0.47 milliampere. Okay, right? Of course, IE, you just try to add this together, you will have your value of IE. So having this value, you can calculate beta, right? Beta will be now equal to 0.47 exponent negative 3 divided by 1.5 exponent negative 6, which is micro, will give me 313, right? 313. This is our beta in practical. So now let us try to measure now what is the voltage BB, BE, BC. So let us try to put correctly. So I'm going to transfer this. This is my multimeter now. Now this is our DC voltage. What is my BB? BB from here. So from this ground up to the base here. What is my BB? 1.087. So 1.087. BC 9.4. So BB 1.087. 1.087 and BC is equal to 9.4 volts, right? Then what is my BE? What is my BE here? Let me just measure. So from here up to here, this is my BE equal to 0.467 volts. 0.467 volts. BE is equal to 0.467 volts. So now let us go beyond. Let us try to measure BCE. We can calculate BCE, or otherwise we can measure what is the voltage BCE. So this can easily identify if it is in active mode. 8.93. Okay, BCE is 8.93 volts. That means this is in active mode, right? We have these readings. IB is 1.5 micro. IC, we have beta. BB, BC, BE, BCE. Here you can calculate IE with these values. Okay, so now let's try to complete the table. Okay, we had first we had to put our frequency 50 kilohertz, and of course our input is 10 millivolt peak to peak. So let us try to set from our function generator here. Let me just show you. Okay, so our input amplitude here will give me 10 millivolt. I'm selecting this millivolt. Okay, and then for frequency, I'm going to start with 50 hertz, right? 50 hertz. So what happened now? This is the output at 50 hertz. Okay. Now the issue is on the oscilloscope. Now let us try to do the measurements. Frequency, okay, and then amplitude, B peak to peak of the source, and B peak to peak of the output. Now acquire normal high resolution. Okay, what is the reading here? So you have here a 10 volt input, and the output is 284. So I have 284 millivolt output. Then you can calculate the gain. So my output here is 284 millivolt at frequency equal to 50 hertz. So I'm going to change the frequency now to 100 hertz. 100 hertz. So I'm going to change frequency to 100 hertz. Okay, and then reset auto. We will have then acquire. Okay, it's normal, high resolution. What is our reading now? 387. The output is 387, right? Okay. Now let us try again to change the value of the frequency to what? 200. So 200. I'll just rotate this 200. So what's the reading? 425. Okay, 425. Later I had to focus this one. You cannot see in your lab report. Okay, this is of 425 at frequency 200. 425 millivolt. I'm going to increase now this one to 300. So just increase to 300. Look at the frequency. Frequency is showing here 300. Okay, what is the output? 431. 431 is the output. Next is 500. Next is 500. Look at this one. Try to focus on this one. This is, we are adjusting the frequency, and this is the output. So we have here 500. So at 500 now, the output is 444 or 437 here. So millivolt, 437. Still small. Now next frequency here is 1K. So I'm going to press now on frequency 1 kilohertz. Okay. Then press auto. Press auto here, then acquire normal, high resolution. So we will have a 450 millivolt output. Look at this output at 1K, 450. So at 1K, 450 millivolt. The next value will be 50K. So the next value is 50K, 50 kilohertz. Okay, then press auto. So as you can see here, acquire normal, high resolution. What is the voltage now? It is stable at 437, more or less 437 or 450. Okay, let's try. I'm going to write 450. And then next frequency is 100K, right? Now we are in 100K frequency. So 100 kilohertz. So look at the frequency here, 100 kilohertz. And look at this one. It's just same value approximately. I'm going to write the 412 there, 437. It's fluctuating. So I can say it's 437. All of them, 437. This also. Let me erase. 437. 437. Okay, I have. So 437, all of them. At 500, at 50, 100K, then 200K now. It's now we are in 100K here. So we will have 437. Let me just exchange this frequency to 200 to obtain the reading. 200 kilohertz. So what happened? Now it's try to reduce the output. Let's say 380 millivolt. Okay, let us now change to 300K, 300 kilohertz. Okay, this is 300, guys. Now it's 320. The output is 320. Okay, what is now another frequency? I'm going to increase this frequency from 300 to 400. Okay, 400. Now it's going down. Look at high frequency. The gain is going down, right? 262 millivolt, and 1 megahertz. So we have 1 megahertz here and 2 megahertz. So we will set our frequency 1 megahertz. Auto. What happened now to our output? Normal, high resolution. So what happened now to our high? It becomes what? 100 This is the input. It becomes what? 130. It's fluctuating. Let's get the average. Let's see. Average. Okay, 125. So now at 1 mega, 125 millivolts only. At 2 mega, let's go to 2 mega here. What will be our value? 2 megahertz. Look at what happens, 74 only. 74, this is the output. So if you're going to plot this, the waveform, this values, it will appear like this, right? So if you're going to plot this, I'm going to show you how to simulate it in PSPice, okay, in the next short video, and how to identify the values. So this is our result. Our results here. Okay, calculate the gain for each value. Our input is 10 millivolt, peak to peak, and this one here is all of them peak to peak. Okay, what's next in our experiment? There's no more. We have done everything except for the PSPice. I'm going to we did the simulation in the last experiment, right? Okay, we already did the simulation for different values, so I think no need for me to simulate this one. You should simulate this, and in your report you have to plot the waveform, right? You have to plot the waveform and try to compare your results if it is matching with this practical values. Okay, let me just have this one for you to see everything. Okay.